Good morning, students. We'll continue our chapter that is chemical bonding and molecular structure. Yesterday we have done about the theories which tell us about the geometry of a molecule. The theory was Vesper theory and we have done the concept of overlapping. Before going further to the overlapping topic, I just want one more theory to discuss with you, that is valence bond theory. So students, according to valence bond theory, which is being given by London and Hitler, and it was modified again by Pauling and its co-worker. And this is based on the concept of atomic orbitals and also on the atomic orbital configuration of an atom. Suppose we have an example of hydrogen molecule, right? When hydrogen atom combine, it form a molecule, one H plus another H forms H2 molecule. And this, after reacting with each other, when these two atoms combine to form a molecule, some energy is being released. And this shows that the energy of hydrogen molecule is less as compared to hydrogen atom, right? Because when the hydrogen atom, if I talk about the hydrogen atom which are combining to form molecule, the energy is equal to 433 kilojoule per mole. And it means that the energy of hydrogen molecule is less than as compared to the hydrogen atom. This theory is basically based upon the two forces of attraction. One is attractive forces, the another is a repulsive forces. It means the nucleus of one atom is attracted towards the electron of the other and vice versa. And in this process, the energy is released in attraction. Similarly, the second point indicates you the nuclei of the atom as well as their electrons repel each other. It means molecules, when any molecule form, there are the two types of forces responsible for that. One is the attractive forces and second is the repulsive forces. Students, if the attractive forces are more as compared to repulsive forces, the energy, it means the energy decreases, system energy decreases, and the molecule becomes stable. It means valence bond theory directly or indirectly explains us about the stability of a compound, right? Like question comes, why hydrogen exists in the form of H2 molecule, whereas helium do not exist as He2 molecule. So the simple is the answer. If I'm talking about hydrogen molecule, how hydrogen atom exists, how H2 molecule exists, right? Because the attractive forces between the H and H atom is maximum as compared to its repulsive forces. Therefore, that molecule exists. And when two hydrogen atoms approach either other, the overall potential energy of the system decreases. And hence, a stable molecule of hydrogen get formed. Whereas, if I talk about helium, helium only exists in the form of He, not He2 molecule exists. Because if I talk about the attractive and repulsive forces, the new attractive forces are less as compared to repulsive forces. It means repulsive forces are more than the attractive forces, therefore the molecule of helium is not formed. Right, students? Now come to the concept of orbitals. Yesterday I have talked about the overlapping of orbitals. There are two types of bond which is formed by the overlapping. One is sigma bond and the second is a pi bond, right? And this hybridization topic is based upon overlapping only. What do you mean by hybridization? Students, we knew about the hybrid. When a red color is mixed with a white color, a new pink color is formed. It means pink color is a hybrid of red and white color. Similarly, in chemistry, when one orbital mixes with the another orbital, why there is a need to mix the orbital? Because they are having slightly different in their energies, so as to make them same in energies, right, and shape, we have to mix the orbital, and this phenomena of mixing is known as intermixing of atomic orbital is known as hybridization, and the new orbits that are formed, they are known as hybrid orbitals. So here's the definition. Hybridization may be defined as the phenomena of intermixing of atomic orbital of nearly the same energy belonging to the different subshells, so that to redistribute their energy and to make their shape, the new orbital shape, equivalent in energy and equivalent in shape. For example, if one s orbital reacts with one p orbital, the shape of s orbital is spherical and the shape of p orbital is what? We have done that, dumbbell, right? We have done this in our second chapter, the shape of orbitals. So when the two orbitals combine, what happens, students? They are of different energy, they are of different shape, that is of dumbbell shape, and the first one is of spherical shape. But when they mix together, they form a same shape. There is nothing to be different in the shape, only the one shape is being formed. And there are certain conditions for the hybridization, that number of hybrid orbitals must be equal to the number of combining orbitals. See, there are few points. Mix at least two non-equivalent atomic orbitals, suppose s and p, because mixing requires at least two orbitals. Hybrid orbitals have very different shape from the original atomic orbitals, but that shape is equivalent in energy, right? Number of hybrid orbitals is equal to the number of pure atomic orbital used in a hybridization process. Covalent bonds are formed, right, by overlapping of hybrid orbital with the atomic orbitals and overlap of hybrid orbitals with other hybrid orbitals. It can be possible, right, students? There are few more conditions, that only the orbitals belonging to the same atom can take part in hybridization. The orbitals that participates in hybridization should have only small energy difference, right? And the promotion of electron is not essential condition to the hybridizations. I think the hybridization concept is clear, and see the few examples of hybridization and the types of hybridization, students. There are various types of hybridization involving s, p, and d orbitals. I'm not using F here because only these types of hybridizations are there in your syllabus. The one is a sp hybridization. Sp hybridization is a type of hybridization in which one s orbital reacts or mix with one p orbital to form sp hybrid, and the type of hybridization is known as sp hybridization. sp2, when one s orbital and two p orbitals they mix together, it forms sp2 hybrid orbital, and the hybridization is sp2 hybridization. Third is sp3, again when one s and three p orbitals they combine together, they form sp3 orbit, they form sp3 hybrid orbital, hybrid, and the hybridization is known as sp3. Similarly for sp3d, similarly for sp3d2. Now see how they formed. What are the shapes? See here, suppose we take one example of BeCl2. First of all, write down the atomic number of beryllium. Here the atomic number of beryllium is 4 and the configuration is 1s2, 2s2. I just took a last configuration. One condition is there. Hybridization is possible only when there is a half-filled configuration. अगर atomic orbital पहले से ही complete है, तो element जो है दूसरे एलिमेंट के साथ रिएक्ट नहीं करेगा, right? Here the 2s orbital is almost filled, completely filled. It means वो अपने साथ Cl2 को attach नहीं करेगा. But what happen when the excitation phenomena occur? What is excitation phenomena? When a electron gain some energy or will give some energy to the electrons, it jumps from ground states to excited state. So after promotion, it get promoted, it means. So after promotion, by gaining the energy, the electron jump from 2s orbital to 2p orbital. Now we have two unhybridized orbitals and it can take participate in hybridization. See the shape of 2s orbital here, the shape of 2s orbital, students. You can see the shape of 2s is spherical, 2p is dumbbell. You can take any axis, x axis, y axis, or z axis of 2p orbital. After hybridization, the shape comes out to be linear shape and the angle is 180 degree, right? Yesterday we have done in the valence shell electron repulsion theory that when two when two atoms combine with a central atom, they form a linear shape and the angle is 180 degree. Only the difference is that there we are using the number of electrons and here we are using the orbitals, nothing else. Rest the theory is same. See the second example, students. sp2. Again, sp2 is a similar as that of sp. Here I have taken one example of bf3 molecule, right? And in bf3 again, if I'll write the configuration of boron, boron is 5. Again, you can say 1s2, 2s2 and 2p1. Here we have only one electron, half-filled electron or unhybridized electron in 2p shell, but three atoms has to be combined, three fluoride ions, right? So it means three half-filled orbitals is to be needed. So promotion occurs. After promoting, after going to excited state, now three hybrid orbitals are there, unhybrid orbitals are generated, and see the shape. Here, when 1s and 2p orbital combine, the shape comes out to be trigonal planar, that is triangular shape, and the angle is 120 degree. Same as in the case of sp3 students, the shape comes out to be when 1s and 3p orbitals combine, the shape comes out to be tetrahedral in nature, as in the example of methane. Other few examples showing sp3d. Here we have taken one example of PB5. Again, the same concept. First of all, write down the electronic configuration of phosphorus, that is 15. It comes out to be 3s2, 3p3. But how many atom has to be attached? 5. But I have only 3 half-filled orbitals. Now, again the excitation occurs and one electron jump from s orbital to d. After jumping, I'll get the 5 half-filled orbitals, right? Half-filled. So they will combine with the 5 bromine atom and they form this type of shape, and you know that this type of shape is known as trigonal bipyramid. The same as in the case of sp3d2, the example is SF6, sulfur hexafluoride, octahedral shape is there. Now the molecules, hybridization, the molecules containing double and triple bond, students. This is very important because here sigma bond is formed as well as a pi bond is formed. You can see the example. Here's a, first of all, I'll talk about the example of C2H4. And you know that C2H4 consists of one sigma bond between C and C and one pi bond, right, students? One pi bond is there. I've shown the picture. See, the hybridization is taking place. Similarly, for sp hybridization, here we have two. After promotion, we have two unhybridized orbital, that is 2py and 2pz, and you can see here we get a cylindrical shape of ethyne molecule. You can see this type of shape. See, we have sigma bond between C and H, and we have one sigma bond in C and C, and two pi bonds are there, which is shown laterally. I have shown, and side by side overlapping I have shown the sigma hybridization. Just go through this topic from the book also. If you find any problem, you can ask me. Now, the last one is how to predict the hybridization of a central atom, students. Here's the formula. Suppose X is any element, and it is, if I want to find out the hybridization of any element X, that is equal to half number of valence electrons of central atom plus monovalent atom minus charge on cation plus charge on anion. So there are some example. If after using this formula, the number of bonded atoms comes out to be 2. 2 means the hybridization is sp. Examples are there. If 3 number of atoms come out to be 3, the hybridization is sp2. If 4, sp3. If 5, sp3d. If 6, sp3g2, and so on. Thank you very much.